Hello everyone again and welcome to my channel. On our previous video we explored the first case of a particle in a one-dimensional space, which is translational motion, where we realized that the energy is non-quantized one. Two, we know that the quantum wave function that is exponential has a similar plot to that of the cosine function 2, and finally we have the probability, which is equal to 1, which results in no node, which is 3. Now in this particular video we will look at the second case of the particle in one-dimensional space, which is free particle with a finite with barrier. Now in this particular part we kind of drawn or represented as this over here, where we have our barrier which is in between two space systems. Here we have potential energy to be equal to 0 at the ground level, but when you move to a higher values of y, what we realize is that we do have a maximum potential, which is this V naught over here. Now take note that we have three regions or three zones in here. We have zone 1 and zone 3, which are actually the same in this particular case. They are all free space. However, zone 2 is actually a barrier that you have to overcome. Kind of similar a little bit with our first case, which is a particle in a box, where our particle is actually trapped in this particular region. But take note that this region over here was actually a space. However, in this particular case in here, it's actually a barrier. So I want to say what will happen if we put a particle in zone 1 and moving towards this particular region. What are the possible things that will happen both classically and in quantum mechanics? Now take note that if you're looking at the kinetic energy in this particular case, in zone 1 we should have a high kinetic energy with a 0 potential energy in here. As we move to zone 2, we have our maximum potential energy in here, and finally in zone 3 we have a high kinetic energy. Now in this particular part, let's start off with when we actually place a particle of a mass m and energy in this particular step over here. So our particle is shot into this particular system from zone 1 to zone 2, and what we realize is that looking at it first classically, we recognize that if our energy is actually less than that of the potential energy, which is this maximum, so if our energy of this particular ball over here is less than the potential energy of this particular barrier here, what we realize is that what is going to happen is that there is a reflection where all, take note, of our particles will actually deflect backwards. However, the other case is when we have our energy of our particle to be greater than our potential energy. What we realize is that actually all our particles will pass through our barrier from zone 1 to zone 3 in here. So now in this particular case, what will happen, or going from classical to quantum mechanics. So for our quantum mechanics, we take into account our wave function, which is what we used in our previous video for a particle in a free space without any barrier at all. And in here we're looking at the positive direction of our particle moving in the x direction in here, where we have our exponential, which is similar to what we have in our cosine wave function in here. And what we realize is that first, if we have our energy to be greater than our potential energy of our world, what we realize is that some of our particles which are actually moving in a sinusoidal function in here will make an exponential decay as it enters the barrier, and once it comes out there is a decrease in the amplitude in here. Now take note that what is happening in this particular case is that an infinite chance of reflection at each boundaries in zone 2 will actually occur in this particular step over there. Now this particular region over here is representing our wave function, which is a positive wave function which slightly stretches our exponential function in here. So this depends on the thickness of our boundary over here. And now in this particular part in here, which is our region or space, let's say our box here, our box region over here shows that our amplitude decreases because some particles never make it through. So that is the case for where we have our energy to be greater than our potential energy. Now the next one we're going to look at is a case where we have our energy to be less than our potential energy in here. So our potential energy, which is the boundary in here, versus that of our energy of our particle. And what we realize is that, oh, actually our particle will actually exhibit tunneling, which is a quantum mechanical effect over here. And this tunneling actually reveals that, oh, actually for particles that are seen to tunnel through the barriers, the amount of tunneling actually depends on the following properties, which are as follows. First, higher barrier of our potential energy, which is with respect to our y-axis, lead to less particles tunneling through this particular barrier over here into zone 3. Now next one in here is that the wider the barrier, which is the increase in our L value, this leads to more exponential decay in our curve, which is this particular curve over there, thereby causing or resulting in less tunneling effect over there. And finally, what we realize is that the less massive the particle is, the more particles will tunnel. So this is actually applicable to isotopes, like for example the case of hydrogen. And we realize that for a proton transfer, the rate of a proton transfer reaction is actually related to the size of the hydrogen particle. So if we substitute a proton for a deuterium, what we realize is that the rate of reaction of deuterium is slower than that of a proton transfer. The reason why is because the proton actually passes through the activation barrier. So if we have our activation complex in here that is being formed, this is our reaction where our hydrogen here is going to B. So this is our first one, B being formed and A being generated. So in our first part here, if we have hydrogen 1, then so hydrogen 1 will tunnel through, thereby having an increase in the rate of reaction for hydrogen 1. However, if we have a hydrogen 2, which is deuterium, then they will rather overcome this particular barrier in order for them to actually make it to its product over there. So in conclusion, what we say is that the bigger or massive the atom, then the less likely you'll be able to perform tunneling in various reactions. So all this saying, that's about it for this particular video. I hope you're able to understand this. Please hit the comment down below, let me hear your thoughts. Hit the like, share and subscribe. By that way I can talk to you all later. Be smart.